Ladies and gentlemen, you are welcome. So, this is our first lecture series on uh, post UTME. So, we are going to have a different series of lecture for this coming post UTME. So, we are going to have the first lecture series on chemistry. So, we are going to be solving past question paper, and we will also be adding explanation in each of the questions that we are going to solve. So now we are actually having a question like this: a certain compound on analysis, it gives 2.02 gram of carbon, and then 0.35 gram of hydrogen, and 2.68 gram of oxygen. Then if the molecular mass is 90, what is the A, the empirical formula of the compound, and then B, the molecular formula of the compound? So I think, ladies and gentlemen, this is not actually a difficult question. So we need to understand the basic concept behind the empirical formula and then the molecular formula. When we say empirical formula, it is a formula that shows the exact ratio of element that is present in the compound. And that is what you call empirical formula. It's a formula that trying to show the exact ratio of the elements that are present in the compound. And then we have molecular formula, which show the exact number of elements that are present in a compound. Like, for example, let's say we have something like the CH2O. So this CH2 can be described as an empirical formula of a compound like this. Like, for example, the ratio of carbon, how many carbon do we have here is 1, and how many hydrogen do we have here is 2, and how many oxygen here we have is 1. So we can now say ratio 1 is to 2 is to 1. And this is to tell you that from here, we can see that this is the exact ratio of the element that are present in the compound. The ratio of the element that are present in the compound is 1 is to 2 is to 1. And that is what describes the empirical formula. So this is the empirical formula of the compound. And of course, to know the exact number of elements, we usually calculate n from this empirical and molecular formula. And this n is actually a whole, is usually come as a whole number. Let's say here it is 6. So if we are able to get our number or our n here to be 6, so we can simply calculate the molecular formula of the compound. And how do we do that? It's simple. We have a relationship that gives us exactly which is the molecular formula. Molecular formula, as we can see from here, it is the same thing as empirical formula. Empirical formula. Then we close bracket, and then we have n here. So let's see, the empirical formula here is CH2. So for we to calculate the molecular formula is actually simple. We can now say from here, to get the molecular formula MF, molecular formula, we can now say that the empirical formula is CH2O, then we close it, and then we have N. So the N here is 6, so we have 6 here. So we can now say 1 times 6, so we have C6, we have H times 2, we have 12, we have 1 times 6, we have 0.6. So this is the exact formula of the compound, the exact number of the elements that are present in the compound. So this is molecular formula. So empirical formula is a formula that shows the exact ratio of elements that are present in a compound, while molecular formula is a formula that shows the exact number of elements that are present in a compound. So now let's look at this question and solve it, and from here we'll be able to calculate the molecular formula and the empirical formula. So it's simple. We need to know that each of these elements, they have their own molecular formula. they have their own, yes, they all have their own molecular mass. For example, the molecular mass of carbon is 12, the molecular mass of oxygen is 16, and then the molecular mass of hydrogen is equal to 1. So this is the the molar mass, the molecular mass of each of these elements. So we are now going to take carbon first. We are going to take carbon as this, and then we are going to take hydrogen here, and then we have oxygen. So how we have carbon, and the mass of carbon from here is 2.02, and then in gram, and then the mass of hydrogen is 0.35 gram, and then for the oxygen is 2.68 gram. So what are we going to do? So the first thing to do, we have the mass of each of these elements. So we are now going to see divided by the mass of carbon, which is divided by 12. The mass of hydrogen is 1, so divided by 1. And then the mass of oxygen divided by 16. So what are we going to do? So after having this, we are now going to take we are now going to divide each of this and get the answer. So it is simple. We can now say 2.02 divided by 12, and this give us 1 point. This give us 0. It give us 0.163. And then for this, if you divide this by 1, it will give us the same thing. So we have 0.35. And then the next thing, we are going to also divide 2.68 divided by 16. And this will also give us 0.168. So from here, ladies and gentlemen, without wasting much of our time, we are now going to look at the smallest number among all this. Which one is the smallest? So if you can see, ladies and gentlemen, this one and this one, they give almost the same thing, and they are the smallest. If you look at them from here to here, you'll realize that this 0.16 is the smallest number. So we're now going to divide this by 0.163. Also, we divide this by 0.163. We also divide this by 0.163. So if you now take this one, we divide it by this, is going to give us 1. And if we now take this and we divide it by 0.16, 0.35 divided by 0.163 is going to give us 2. And this one divided by this is going to give us 1. So I think, ladies and gentlemen, without wasting much of our time, you can see that clearly we were able to get the ratio of each of these elements. So therefore, from here, we can simply get the empirical formula, the empirical formula. And how do we get the empirical formula? The empirical formula is now going to be carbon is 1, so it's going to be just C. Hydrogen is 2, so we have H2. Oxygen is 1, so we are going to have this. So this is the empirical formula. So from here, we are able to answer A. So then the next thing is B. So to calculate the molecular formula, to calculate the molecular formula, it's simple. We are now going to say molecular formula is equal to EM. EM means empirical formula times N. So therefore, our empirical formula is going to be, the molecular formula is already giving us 90, if you can look at it. Sorry, the molecular mass of the compound. So sometimes you can write molecular, because for the molecular formula, because we don't have the formula, but we are given the molecular mass already here. So we have it as 90. That is the molar mass of the molecular compound, because we don't, of the compound, because we don't know the compound exactly, but the molecular mass of the compound is given as 90. So here we are going to have 90. And then the next thing is the empirical formula, which is CH2, and then we have N. So we now have 90 is equal to, we are now going to take the mass of carbon is 12, and how many carbon we do have here is 1. So we are going to have a small bracket like this, and then, okay, here there is oxygen. So how many, the mass of hydrogen is 1, and how many hydrogen we have here is 2, then plus, we have oxygen. So the mass of oxygen is 16 times 1, and this is going, sorry, here is 1. And we have the big bracket, and that will give us F. So we now have 90 is equal to 1 times 2 is 12 plus 2 making 14, and then 14 plus 16, this will give us 30. So we now have 30N. So since we have 30N, we can now divide this through by 30. We can now divide this by 30, and this will now cancel this, and at the end we are going to have the value of N. N is now going to be 3. So since the N is calculated as 3, so we can simply get the molecular formula of the compound. And how do we do it? Since we already have CH2E, and then we have N here, then we are now going to have, because here is molecular formula MF. So the MF molecular formula is going to be, because here is 2, so we are now going to put the 2 here, and then so we have 2 times 1, we have C2, then H times 2, because we have 2 times 2 here, so we have H4, and then we have 1 times 2, then we have O2. So the molecular formula of the compound at the end, we have C2H4O2. So this is the molecular formula of the compound. So I hope, ladies and gentlemen, this looks very simple. And please, ladies and gentlemen, don't forget to subscribe, join and follow my YouTube community for more videos. So let's look at another question and solve. So let's look at another question, question 2. Calculate the current that must be passed into a solution of chromium-3 salt for 1 hour in order to deposit 1.2 gram of chromium. So now, ladies and gentlemen, how do we solve this question? It is also very simple, and it falls under electrolysis. And don't forget, ladies and gentlemen, when we said electrolysis is a chemical decomposition of compounds into their component ions by passing an electric current either in a solution or in a molten form. Let's say electrolysis is a chemical decomposition of compound. Let's say you have sodium chloride. So the word lysis means breaking down. So electrolysis, it means is the use of an electric current. It's the use of electric current to break down compound into their component ions. So when you apply an electric current, either in a solution or in a molten form, it will break down compound, we call them electrolytes, into their component ions, like sodium ion and chloride ion. So the sodium ion is cation ions, they are positively charged ions, while anions, they are negatively charged ions. So during this electrolysis, while breaking down the compound into their component ions, usually there is a loss of mass. There is a loss of mass, and that loss of mass is described by Michael Faraday. Michael Michael Faraday in the year 1833. So he actually come up with a law, which we call them Faraday's law of electrolysis. So we have first law, we have second law. So under first law, according to the Faraday's law, he stated that um, the mass of an element discharged or deposits during electrolysis is directly proportional to the current applied. So it means that the mass of an element that actually deposited during electrolysis is directly proportional to the amount of electric current you apply. It means that the quantity of an electricity or the mass of an element deposited during electrolysis is directly proportional to the quantity of the electricity applied. So it means that the higher the mass deposited or discharged during electrolysis means that the higher the electric current that is applied. So that is why there is a strong relationship between the mass and the quantity of electricity. So the first Faraday's law of electrolysis is the law that try to demonstrate that. So now, without wasting much of our time, let's see how we are going to calculate this. So first, you have aluminium salts. So you have chromium salt, which is Cr, and this Cr during electrolysis, it loses electron. It loses an electron. So remember, chromium is an element that can have a variable oxidation number. Chromium is an element, is actually, it is a transition element and they usually have a variable oxidation number. So in this case, what we are going to do, we are to calculate the quantity of electricity that is actually deposited during this electrolysis. So to do that, we need to first calculate, because there is a formula, this Q, which is quantity of electricity, is equal to IT. And from these questions, from here, we doesn't have quantity of electricity. So therefore, we have to calculate the quantity of electricity. And how do you calculate the quantity of electricity from here, ladies and gentlemen? So now, from here we can see that chromium 3, it means that it is chromium 3 plus, because generally chromium can have an oxidation number of +1, it can be +2, +3, +4, +5, because they generally have variable oxidation state. So generally during this electrolysis, we have chromium 3, which actually accepts 3 electrons to become neutral chromium. So therefore, from here, we can see that the number of Faraday, we have 3 Faraday. So the number of Faraday depends on the number of electrons that is received, or the number of electrons gained by a particular ions to become neutral, or by a particular element to become neutral. So therefore, here, because chromium accepts 3 electrons to become neutral, so it means that it's going to be 3 Faraday. And of course, 1 Faraday is something as, so I'm now going to say 3 times 1 Faraday is something as 196,500 column. So 1 Faraday is 196,500 column. So here we have 3 Faraday. So that is why we are going to multiply it by 3. So now, if we multiply 3 times 19, if we multiply 3 by 196,500, what are we going to have? So let me see. We have 3 times 196,500. So we multiply 3 times 196,500. So the constant is, sorry, it's not 196,500, it's 96500 column. So this is a Faraday's constant, column for mole. So therefore, we now have 3 times 96500, and that will give us 289. We have 289,500 column for mole. So therefore, now the mass of the element that is, or the charge during electricity, is 1.2 grams. So we are now going to have a relationship So we have 289,500 column. So we are now going to relate it with the mass of the element, which is 51 gram per mole, and this one is column per mole. And then, of course, for the quantity of the electricity that we want to get, which is Q, is unknown. So we are going to relate it because, as we said, the mass of the element discharged during electrolysis, it's depend on the quantity of the electricity applied. So now, how many or what will be the quantity of the electricity use when you have 1.2 gram of the mass deposited? So we are now going to cross this. So how are we going? We are now going to cross multiply. So when we cross it, we are now going to have this time this and this time this. So we have Q times 51 is equal to 289,500 times 1.2. And what we are interested is to get Q. So divide both sides by 51 by 51. So this one will now cancel this, and we now have Q is equal to, so we have from here we have 289,500 times 1.2 divided by 51, and this will give us 6,811 column. So this is the quantity of the electricity applied to deposit 1.2 gram. So, but what we are interested is not actually about the quantity of the electricity. We are to calculate current. So therefore, we are going to use this formula. We are now going to use this formula. Q is equal to IT. But the time given is in hour. So we have to convert it to second. So we have the time given, the time T is given in hour. So we have to say 1 times 60 times 60. So 1 times 60 times 60, this will give us 1 times 60 times 60. This will give us, the time is now going to be 3,000. We have 3,600 seconds. So therefore, we now have Q is equal to IT. So the Q is 6,811 is equal to the I times the time is 3,600. 3,600. So we now divide this by, we can now divide 3,600 both sides. So this one, 3,600 both sides. So this one will now cancel this. And at the end, we are now going to have our I. So our I is going to be 6,868. We're now going to have 6,811 divided by 3,600. And this will give us 1.89. We're going to give us 1.89 ampere. So we can now come back and check the option. Option A is 3.5, option 2 is 2.3, option C is 1.89, and then last option D is 1.52. So the answer is 1.89. Please, ladies and gentlemen, if you enjoy this video, please subscribe and join to my YouTube community. Please comment on the video if you like more of this video, then we will actually release more of it. Thank you very much, ladies and gentlemen, and see you next